everyone. Today we would like to discuss about center of mass. The center of mass of an object is the mass-weighted average position of all mass of an object. For an object with a constant density and symmetrical shape like a ball, the center of mass is directly in the center of the object. The center of mass of constant density sphere is directly in its center. Okay, please observe this animation. The ball is moving in a projectile motion. The shape of the path created by the ball moving in projectile motion is a parabola. To be specific, the shape of the path created by the center of mass of the ball is a parabola. Now, please watch what happens when we add a racket moving in a projectile motion. The motion is a little bit complicated here. The racket rotates around its center of mass. However, if you observe it more detailed, the motion of the center of the mass of the racket still follows a parabola just like the ball. In other words, we can treat the racket as if all its mass were located at the center of mass and consider the force of gravity to be acting at the center of mass, just like it does for the ball. Maybe some of you will ask, are the center of mass and center of gravity the same? Well, as long as the object is in a constant gravitational field, the center of mass and the center of gravity of an object are in the same location. The phenomena that we have observed are all happening in the Earth. And we know that around the Earth, the gravitational field is relatively constant. That is 9.8 meters per second squared. Hence, we can conclude that the center of mass and the center of gravity of those objects are in the same location. Now, please observe more examples in the video, and also please pay attention to the frisbee ring. The center of mass of those objects make path with shape of parabola. The center of mass of an object is not necessarily located at the object. For example, as frisbee ring. You have observed in the previous video, the frisbee ring has center of mass that is located in the geometric center, which is not actually on the ring. This works for system of objects as well. For example, we can have three balls of moving in projectile motion. Even though those balls are moving relative to one another, they still have a center of mass which moves in a parabola in projectile motion. Please observe the video. When I apply a force on the rod to the left of the center of mass of a system, the applied force rotates the system. Then, when I apply a force on the rod to the right of the center of mass of the system, the applied force rotates the system in other direction. And then, when I apply a force on the rod at or directly toward the center of mass of the system, the system does not rotate. If we apply a force to an object at or directly toward its center of mass, the force applied will not cause the object to rotationally accelerate. However, the force will only cause a linear acceleration to the object. Now, we want to discuss about how to determine the center of mass of a system that contains of some point particles. But beforehand, I would like to explain what is point particle. Point particle is object that its size is quite small compared to the whole of the system. Because the size is small compared to the whole of the system, we may not consider its shape. So we just consider it as a point. Okay. Now look at this example. In this example, we have 3 point particles which has mass of m1, m2, and m3. Okay, to determine the coordinate of the center of mass of this system, we can use this formula. So the x coordinate of the center of mass will be equals to m1 times x1 plus m2 times x2 plus m3 times x3 divided by m1 plus m2 plus m3. Again, m1, m2, and m3 are the mass of the particle 1, particle 2, and particle 3 respectively. Meanwhile, x1, x2, and x3 are the location or the x coordinate of the particle 1, particle 2, and particle 3. But now, if we have n number of particles, the x coordinate of the center of mass can be determined through this formula. This formula is just the extension of the previous formula. So when we have n numbers of particles, the formula becomes m1 times x1 plus m2 times x2 plus and so on until plus mn times xn divided by m1 plus m2 and so on until plus mn. And this formula can be shrunk into this kinds of notation. Yeah. So the x coordinate of the center of mass is equals to the sigma or the sum of mi xi divided by the sum of mi. Again, mi is just the mass of each particles and xi is the x coordinate of each particle. Meanwhile, the y coordinates becomes like this. So to determine the y coordinate of the center of mass, the formula is similar, which is equals to the sum of mi yi divided by the sum of mi. Okay. But if we have three-dimensional objects or three-dimensional system, usually we add one more that is z coordinate of the center of mass. And this formula is also similar. The z coordinate of the central mass equals to the sum of mi times ci divided by sum of mi. Now, if we have objects that is continuous and homogeneous, we can determine the center of mass by using calculus. However, we won't discuss it here. Yeah, because I believe that you have explored how to determine the center of mass or centroid of some regular and continuous uh, homogeneous objects in the calculus or in the other courses. I wouldn't explain it in this course, but I just want to remind you several center of mass of some regular, continuous, and homogeneous objects. Okay, some of them are depicted in this figure. Okay, so for example, for semicircular ring, yeah, the center of mass is located in this point, which is located at 2r divided by pi from the horizontal plane. Here r is the radius of the circular ring, okay? And then for semicircular disc, the locations of center of mass is here, which is located about 4r divided by 3 pi from the base of the circular disc. I mean the semicircular disc. And then for semi-hollow sphere, the location of the centroid or the center of mass is here, which have a distance of r divided by 2 from the base. So this length is r divided by 2. And then for semi-solid sphere, the center of mass is here, and this length is 3r divided by 8. Again, r is the radius of the semi-solid sphere. And then for hollow cone with the height of h, the center of mass is located at this point, and this point has a distance of h per 3 from the base. So this distance is h per 3. And then for solid cone with height of h, the location of center of mass is here, and this point has a distance of h per 4 from the base of the solid cone. And finally, for triangular with height of h, the center of mass is located here, which has a distance of h per 3 from the base of the triangle. Okay, so this length is h per 3. Okay. For the rest of objects, you can find out in the book. Okay, let's discuss some example. Yeah. Here we have 4 point particles, A, B, C, and D. Yeah. The mass of A is 100 grams, and then the mass of B is 200 grams. The mass of C is 200 grams, and the mass of D is 200 grams. And they are located at the center, at the corner of a square with h of 10 centimeter. Okay, please keep in mind that one of the particle has different mass. Yeah, if the 4 particles have the same mass, then it's really easy to find out the center of mass. It's just located at the middle. But here the mass of A is 100 and the rest is 200. So we have to calculate it with the formula that we have discussed before. Okay, first of all, that I want to do is make a point of reference. Yeah, and in this case, I will make point A as a reference as original point 0, 0. Well, you can use any other point of reference, but I decided to use A because I think if we use A, the calculation will much more simpler. Okay, and if this point A is origin or 0, 0 reference, then the location of B or the coordinate of B becomes 0, 10. It means that the B has x coordinate of 0 and the y is equals to 10. And then the coordinate of C is 10, 10. Meanwhile, the coordinate of D is 10, 0. Okay, then the center of mass of the system can be determined through the formula that we have discussed before. These are for the x coordinate of the center of mass. Yeah. It's equals to MA XA plus MB XB plus MC XC plus MD XD divided by the total mass. Okay, now what we have to do is just put the known variables to the formula. MA, for example, yeah, MA is 100 grams and XA, the location of point A is at x equals to 0, so XA will be 0. Yeah. And then for particle B, the locations of P is located at x equals to 0, so XP is 0 and the mass is 200. And then for particle C, it's located at x equals to 10. So XC is 10. And then particle D is located at x equals to 10, so XT is 10. And then divided by the total mass. Okay, thus the x coordinate of the center of mass of this system of particles is equals to 400 divided by 700, or equals to 40 divided by 7 centimeter, or 40 per centimeter. I mean 40 per 7 centimeter. And then the y coordinate of the center of mass of the system of particles can be determined through the similar equation, yeah, the YC. And yeah, we just need to put the known variables to the formula, and we'll get the y coordinate of the center of mass is equal to 40 per 7 centimeter. So for example, here is 40 per 7, yeah, and here is 40 per 7. So the location of the center of mass is located around here. Yeah. Yeah, so again, the center of mass is located at coordinate of 40 per 7, 40 per 7 centimeter. Yeah. Okay, if you're still confused with the applications of the formula, you can ask me in the synchronous session on Wednesday. Let's move on to the second example. Here, determine the location of the center of mass of this object. So we have this object. Yeah. This object is actually can be regarded as two objects. The first one is the rectangular, and then the second one is the triangle. And if you look at this object actually has a symmetry with respect to the y-axis. So the x coordinate of the center of mass can be the center of mass. I mean, the x coordinate of the center of mass is right in the middle. So we just need to find out where is the y coordinate of the center of mass. Okay, so here I will draw the Cartesian axis, and I will take this point as a point of reference. 0, 0. Okay, so this object can be divided into two, the rectangle and the triangle. And then we know that the center of mass of rectangle is located at the middle. So located around here, yeah. And this point actually is located 5 centimeter above the base because the length of this is 10. So a half of 10 is 5. So here it's actually 5. And then the center of mass of triangle is here. Yeah. And remember, from the table, we know that the center of mass of triangle is located in the h/3 from the base. Yeah. Okay. And you can see that the height of triangle is in here. Okay, first of all, we need to find out the positions of each center of mass. Yeah. But for triangle, we need to find out the height of the triangle first. Now, in order to find out the height of the triangle, you can consider this right triangle over here. This is a right triangle. The hypotenuse is 25 centimeter. And then the base here is 10 plus 10. So in total is 20. Okay. Then the height can be determined through Pythagoras theorem. Yeah. Using Pythagoras theorem, you can find out the height. The height is 24 centimeter. And thus, this length, the distance of the center of mass to the base of the triangle here is h/3, or 24 divided by 3, which equals to 8 centimeter. Okay, hence, because this line is 8 and this line is 10, then the coordinate of the center of mass of triangle is 0, 18. And then the center of mass of the rectangle here is 0, 5. Okay, now let's determine the location of the center of mass of the system of the whole object. We need to assume that the object is homogeneous. Yeah. And if the object is homogeneous, then the mass is directly proportional to the area of the object. Thus, the formula to determine the center of mass can be modified, can be slightly modified by replacing the mass by the area. So the formula becomes like this. Yeah, A1 times A1 plus A2 times Y2 divided by A1 plus A2. Yeah, A1 here is the area of the rectangle, and then Y1 is the Y coordinates of center of mass of the rectangle, and A2 is the area of triangle. So for A1, yeah, A1 is the area of the rectangle. Area of rectangle will be equals to 20 times 10. Yeah. So we have this one, 20 times 10, and then the Y1 is 5. So we put 5 here. And then for A2, A2 is the area of the triangle. So it equals a half times 40. The base is 40 because it's from here, 10 plus 20 plus 10, so 40. And then the height times the height is 24. Hence, we have this one, a half times 40 times 24. And then Y2 is 18. So we put 18 here. Okay, and then we divide it by A1 plus A2. And if we calculate this number, we will get y equals to 14.47 centimeter. So I guess it location is around here. Yeah, maybe around here. 14.47 centimeter is the center of mass. Okay, that is an example to determine the center of mass of two-dimensional object. In the previous meeting, we have learned about Newton's law in the translational and rotational motion. Do you still remember? I hope you remember this formula. For translational motion, the net force is equals to mass times the linear acceleration, or sigma f equals to ma. I believe that this formula is very popular, so I hope you don't forget about that. And then for the rotational motion, we have the net torque equals to the moment of inertia times the angular acceleration, or sigma tau is equal to I times alpha. The first example that we want to discuss is rolling motion on a horizontal plane. Here we have a ring that goes on rolling motion on a horizontal plane. Rolling motion is actually a combination between rotational motion and translational motion. This ring actually rotates around its center of mass, and at the same time, the center of mass is changed in position. If we analyze the force acting on this ring, we have the gravitational force toward the bottom, and then a driving force toward the directions of the motion, which is going to the right, and also friction between the ring and the horizontal plane. As you know, rotation motion is always caused by torque. In this system, the torque is caused by the friction. The friction acts at a distance of r from the center of the rotation, and hence the torque is equals to r times the friction. R here is the lever arm, or equals to the radius of the ring. And if we combine the equation of torque to the Newton's second law, we will have R times F sub s equals to I times alpha. And we know that alpha, or angular acceleration, is also equals to the A over R. A is the linear acceleration and R is the radius of the ring. And if we modify the equation, we will have this equation. Friction equals to moment of inertia times linear acceleration divided by the radius square. Okay, let's denote this equation as the first equation. And then, because this ring also goes to translation, we have this relation. Net force equals to mass times acceleration. And the force that causes acceleration is the driving force minus the friction. Minus because friction acts in the opposite from the directions of the driving force.
Yeah, we only analyze fx because for fy, the fy is in equilibrium state and hence no motion in the y direction. Okay, this equation f minus fs equals to ma is denoted as the second equation. Now we would like to combine first and second equation, and if we put fs in the first equation to the second equation, we will get this equation, and you just need to modify this equation to determine the acceleration. So you move this term to the left side, and then after that, try to get the A or the expression for A. And finally, we get A is equals to force divided by moment of inertia divided by radius square plus mass of the ring. Okay, applications of Newton's second law to analyze rolling motion on a horizontal plane. Now we'll discuss about the second case, which is slightly more complicated compared to the previous case. The second case is rolling motion on an inclined plane. So again, here we have a ring. The ring is rolling on an inclined plane. And the plane is like this with angle of theta at this corner. Okay, on the body or on the ring, there is gravitational force toward the bottom, which is equals to mass times the acceleration of gravity. And we can split this force to horizontal direction that is parallel to the inclined plane, and the directions that is perpendicular to the inclined plane in that direction. Yeah. Okay. In the directions that is parallel to the inclined plane, we have mg sine theta. Yeah, it is because if you analyze this angle here is actually the same with this angle here. So this element of force is equals to mg sine theta. Meanwhile, in the directions that is perpendicular to the inclined plane in that direction, here we have mg cos sinus theta. Mg cos theta here. And because the string doesn't move in that direction, means that the normal force and this force is in equilibrium. And hence we can determine that the normal force is just equals to mg cos theta itself. Okay, and then between the plane and the ring, there is friction there. And the friction is in opposite to the directions of the movement. Okay, the friction is denoted as Fs. And this Fs actually acts in a distance of r from the center of the ring or center of rotation. Okay, again, this is a combination between rotation and translation motion. The rotation is caused by the friction because the friction acts at a certain direction from the center of the rotation. Translational motion is caused by the driving force mg sine theta, but it is restricted by the friction. So here we can have F equals to ma for the translational motion, and the net force is equals to mg sine theta minus fs. Yeah, so fs acts as restriction. This one is the first equation. And then for the rotational force, again, rotational force is always caused by the torque. So we need to calculate the torque. The only force that causes torque here is just the friction. So here we have R times Fs for the torque. And according to Newton's second law, the net torque is equals to I times alpha, or I times A over R. So we will get this equation. R times Fs is equals to I times A divided by R. Or in other words, we can express the friction as I times A divided by R squared. Okay, let's denote this equation as the second equation. And now let's combine equation 1 and 2. So if I put equation 2 to equation 1, we will get mg sine theta minus I times A divided by R squared equals to ma. And then what you need to do is just move this term to the left side and then try to find the expressions for linear acceleration, or A. And finally, we will get A is equal to mg sine theta divided by I over R squared plus m. Again, m is the mass of the body, or the mass of the ring. Then g is the acceleration of gravity. And then theta is the inclined angle of the plane. And then I is the moment of inertia of the object, or the body, or the ring. And then R is the radius of the ring. And then M is the mass. Okay. Yeah. So you need to pay attention that for this second case, the driving force is actually coming from the force of gravity itself. Meanwhile, for the first example, the driving force is F. For example, you push this ring, so your pushment is actually the driving force. But for this example, there is no pushing. It's just gravitational force. In case you push this ring, then the driving force is the combination between your pushment and also the gravitational force. Okay, for the third example, we have a pulley. The pulley have a moment of inertia of I and radius of R, and it has a certain mass. And then there are two objects hanging on the string. The first object has mass of m1, and the second object has the mass of m2. Okay, so if we analyze here, in the first object, we have weight or gravitational force m1 times g, and then at the second object we have gravitational force of m2 times g. And then in the string right above the first object, there is a tension T1, and then at the string right above the object 2, we have tension T2. And due to those two tensions, there will be torque acting on the pulley, and thus the pulley will rotate. So this example is actually an example of rotational motion. Yeah. So for the rotational motion, we have Newton's second law that said that the total torque or the net torque is equals to the moment of inertia times angular acceleration, or also equals to I times A divided by R. Okay, and the torque here is caused by T1 and T2. And if you look at the T1 and T2, actually the torque caused by them are opposite in direction, and hence we have minus here. Yeah. And because the torque is caused by the tension that is acting on distance of r from the center of rotation, then the magnitude of torque is r times tension 1 at here, and at there is r times the tension 2. Okay, I think I miss writing the r here. I used to use small r because in the equation I put small r. Okay. Yeah, so we can combine these two expression to be T1 minus T2 equals to I times A divided by R squared. And let's denote this equation as the first equations. And then we also have another Newton's second law. The net force is equals to ma, mass times acceleration. And on the first object, the net force is equals to m1 times g minus t1. Because t1 and m1g is acting on opposite direction. And of course, we have m1 times a. Meanwhile, at the second object, here we have T2 minus M2G equals to M2 times A. And let's combine those two equations. Yeah, we can add them all. Okay, by adding them all, we will get M1G minus M2G, then minus T1 plus T2 equals to M1A plus M2A, or we also can write it as like this. And then, yeah, let's modify the equation. Here we have M1 minus M2 times G. Yeah, so I put the G out of the bracket. And then I move the terms T1 and T2 to the other side. So we got this. Okay, let's denote this last equation as second equation. Now we can combine equation 1 and equation 2. So by replacing T1 minus T2 by IA over R squared. So here become like this. Okay, and by modifying this equation, you should find that the acceleration equals to m1 minus m2 times g divided by m1 plus m2 plus I over R squared. So we have applied Newton's second law for rotating pulley. Okay, now let's move on to the kinetic energy. Okay, object that goes on rotational motion has kinetic energy because they actually move. And the kinetic energy for rotational motion is determined by a half times the moment of inertia times the angular speed square, or omega square. And of course, you also have to remember the kinetic energy for translational motion. Kinetic energy is equals to a half times mass times the speed square. Okay, because rolling motion is actually a combination between rotational motion and translational motion. Hence, the total kinetic energy is the sum between rotational motion kinetic energy and translational motion kinetic energy, or K equals to Kr plus Kt. And hence, the total kinetic energy is half times moment inertia times omega square plus a half times mass times v square. There is quantity called angular momentum in rotational motion. So angular momentum is a vector quantity that is defined as I times omega. I here is the moment of inertia and omega is the angular velocity. Angular velocity is a vector, so L must be a vector. Meanwhile, I, the moment of inertia is scalar. Okay, and there is a principle called conservation of angular momentum. When in the system the net torque is zero, the angular momentum must be constant, or I times omega must be constant when the net torque is zero. Okay, guys, today we have learned about center of mass, and then we learned about the applications of Newton's second law on rolling body and also on rotating pulley. We also learned about kinetic energy on the rolling body, and at last we learned about the conservation of angular momentum. I hope you enjoy our learning today. Uh, if you have any question, please leave comments on the LMS Bella. And also you can contact me through WhatsApp, or you also can ask me question when we have a Zoom meeting on Wednesday. Okay, see you on Wednesday. Have a nice day. Bye.